underbalance condition happens. In this formula, the hydrostatic pressure goes less than the pore pressure. So there are some parameters here. The density and the depth. So the density of the drilling fluid, what we are using at that depth, if it is not sufficient enough or if it is not high enough to control the pore pressure, that will cause a kick. The density of the drilling fluid is too low. Instead of using a 9 ppg fluid, if you use a 8.8 ppg fluid, that means a drilling fluid of lower density, it will not give the required hydrostatic pressure to control the pore pressure. So as you go deeper and deeper, you have to keep increasing your drilling fluid density so that the hydrostatic pressure is always more than the pore pressure. That means, in other words, you are giving a small boy a very big job, which he cannot do. So you have to send the correct man, or you have to use the correct mud weight, mud density to control the pore pressures. Next. The next is, we have the depth. We have the depth, feet. That means, even if you have the right density or even slightly higher, if the depth becomes less, what will happen? The pore pressure will take control. The depth is not going to reduce, but the height of the drilling fluid. If you don't maintain the drilling fluid till the surface, the hydrostatic pressure at the bottom will reduce. If the well is only half full, even though the density is correct, the height of the drilling fluid is less. So it is always important to keep the hole completely full so that you get the required hydrostatic pressure. So the major causes is because of not maintaining the fluid density and not maintaining the hole in full condition. So these are the first two causes which will create an underbalance condition and it will cause a kick. Next, for any reason, the hydrostatic pressure is okay with the drilling fluid density and the hole is full. That is when drilling. But when we try to come out of the hole, you remove the drill string for some reason. Either there is a bit change, the bit is worn out, it is not drilling faster. So you bring the BHA, the bottom hole assembly, to change the bit and go back to drill. Or when you reach the target depth, you have to remove the drill string to proceed with the next operation. At that time, when you are pulling the pipe, from the wellbore, if you do it faster, it will create some pressure differences. It will create a negative pressure in the wellbore. Like if you are pulling a straw from the juice bottle, if you pull it very fast, you will see that there is some disturbances. That disturbances is enough to create a kick, or for the formation fluid to become more than the hydrostatic pressure, momentarily, temporarily. But once the formation fluid enters into the wellbore, it will start its job. So it will start contaminating the drilling fluid slowly. It will increase the kick volume. So when I pull the pipe out of the hole, you create a swabbing effect. If the hole size and the bottom hole assembly clearances are very small, when you pull the pipe, you create a negative pressure below the pit. That will cause underbalance condition, which will cause a kick. So when you're pulling the pipe out of the hole, you have to make sure that you don't give a very high swabbing effect. So you don't reduce the hydrostatic pressure. So you have to do calculations and see, this is the speed I am going to pull the pipe, or I should not pull more than this speed. If I do that, because of swabbing effect, I get a kick. Next, again, this is a reduction in the height of the drilling fluid. Not because you have done it. So you have selected a drilling fluid density which is higher than the fracture pressure. For some reason, it is not your fault. But when the fracture pressure at a particular depth is less than what you have calculated, the hydrostatic pressure becomes more than the fracture pressure, either temporarily or momentarily. When the formation gets fractured, what happens? It opens up another flow path. The hole will start, the level will start reducing because the drilling fluid is going onto the fracture side. So when this happens, so whatever fluid you are filling inside the hole is lost in the formation. The condition or the situation is called lost circulation. So you start losing your fluid level. When you start losing your fluid level, the hydrostatic pressure reduces, creating underbalance condition. You get into a kick. This lost circulation may be because of a formation which is already fractured. It is not because of your fault, not because of your negligence. But the formation is such that if you are drilling a well 100 meters away from this place and you have not seen a fractured formation, you cannot take it for granted that it is only 100 meters away from the existing well. There will not be any fracture zones. You may or may not encounter a fracture zone. If you encounter a fracture zone, you may end up in lost circulation and you may get a kick. So this is about reduction in hydrostatic pressure because of the loss of drilling fluid into the formation, lost circulation. Next, you take care of your density, drilling fluid density. The hole is always full. You confirm with the geologist, no fracture zones. You are not pulling the pipe, or even you are pulling the pipe, you are pulling it very, very slowly, so you don't want to keep. But when you are drilling, the formations, when there is a change in formation, each formation will have a different pore pressure because of the characteristics of the rock matrix. If the rocks present here are not permeable, the fluids getting collected here, they get trapped. And the pressure starts increasing here. Because it is trapped here, the formation which is giving out hydrocarbons coming out here will start acting at this place because it is getting accumulated. That is called the overpressured formation, overpressured zone, abnormally pressured zone. That means as the depth increases, if the pressure increases linearly with respect to the hydrostatic pressure of seawater, that is normal pore pressure. So every 100 meters, when you check the pore pressure, if it is following the same line or the hydrostatic pressure line of salt water, that is normal pore pressure. Because it is connected to the surface. The hydrostatic pressure depends only on the depth. But when you say abnormal formation, the pore pressure is increasing linearly. But when you reach the abnormal zone, the pressure starts increasing more. It deviates from the normal pore pressure gradient. If that happens, that means you have to be careful in dealing with these abnormal pressure zones. So the geologist will give you the details. These are the depths where you can encounter an abnormal zone or an overpressured zone. You have to be careful. It is not that you're going to increase your mud weight or going to do any well control measures. No. When you start drilling, you keep looking for the indications. If you start getting indications, that means you have entered the overpressure zone. If you are careless or if you have lost control of your depth, miscalculation, so you enter into the formation without knowing. And if you drill faster, automatically you will get into a kick situation. So these are the 5 reasons, 5 general reasons why a kick happens. Density is too low, hole is not full, a swabbing effect, you create a negative pressure or an underbalance condition because of pulling the pipe, or you enter into a fractured zone and you lost the drilling fluid, lost circulation condition, which reduces the hydrostatic, or when you enter into abnormal zone, you get into a kick. So these are the basic 5 causes why a kick happens, or the causes of kicks. We will assume that a kick has happened. When the kick happens, you need to know how it is going to behave. Because if it is your child, you know how the child will behave if they see chocolates, or if they see a buffoon, if they get into a shopping center. You know about your child how it's going to behave, but someone else will not know. Kick is a kick. So it is the same behavior. How this kick is going to behave when it enters into the well bore. So you have to have knowledge not only about kick, you need to know how it will behave. If it is a water kick, if it is a oil kick, if it is a gas kick, so you need to start identifying, looking for indications, which type of kick has happened. Of course, you do some calculations to identify the kick density, to identify whether it is a water kick or a gas kick or a oil kick. But before that, with the behavior, you can identify. If you know the theory completely. So when the formation fluid enters the well bore, at a rate determined by the permeability of the rock bore. So now here we are getting into more of the rock characteristics. When the kick happens, it is because of an underbalance condition. Whatever reason it is an underbalance condition, a kick has happened. But once the kick has happened, the intensity of the kick depends on the rock characteristics. How well this is connected to the formation below and above, that depends on the permeability. So permeability is the ease of flow of the oil in the formation. If the permeability is more, that means the rock can transmit fluids at a faster rate. So a kick happens at this place. If it is the permeability is very good, the whole formation at that depth, that formation which is there, which is going to keep acting on it. Very quickly, everyone is alerted and then they start rushing into the well bore. If the permeability is good or high. Assume that the permeability of the rock is very, very bad. You get a kick, but that kick is not well supported by the formation. So it will subside. The intensity will reduce. But if it is highly permeable, the intensity will be very, very high. So the formation fluid entering into the well bore, along with the permeability of the formation, decides the intensity of the kick. Next, when the kick gets inside the well bore, how that kick is going to behave. If it is a water kick, the pressure is going to get dissipated in the drilling fluid. Water is incompressible. So the pressure gets dissipated very quickly. So a 5000 psi, when it is let into a 4000 psi, it becomes less immediately. Like, if you have a Coke bottle full of Coke, you open it, if it is only liquid, the pressure reduces faster. If the Coke bottle is half filled and you agitate it and then open it, if it is gas, that's going to be continuously flowing for a longer time. So a water pressure or a liquid pressure gets dissipated faster than the gas pressure. Because liquids, especially water, is incompressible and they don't expand. But gas, they are compressed, they are compressible. And because of the high compressibility, when you get a kick, it starts expanding more and more and aggravates the well-controlled situation very quickly. So if it is a water kick, it is easy to control. If it is a gas kick, it's going to be difficult to control. So you need to understand how gas getting into the wellbore, how it's going to behave when it is traveling up. So when you get into a large shopping center, you might see big aquariums, big fishes, and you can see air bubbles being let at the bottom. And these air bubbles, when they start from the bottom, they are smaller. But as it starts coming up, the size of the same air bubble starts increasing as it comes up. So what happens when the gas is expanding? The pressure reduces. School level chemistry, school level physics is all applicable here. P1V1 is equal to P2V2 at constant temperature. Assuming that we have constant temperature here, the high pressure, low volume gas, when it enters here and it starts moving up, the volume starts increasing because it is expanding. When it is expanding, the pressure has to reduce. So the high pressure, when it comes inside the wellbore, the pressure reduces, but the volume increases. When the volume increases, it displaces more of drilling fluids. More drilling fluid is displaced. So the total height of the drilling fluid starts reducing, and the underbalance condition becomes bigger, and you get a continuous flow of formation fluid into the wellbore. That situation is bad. You are not supposed to allow the gas to expand. You have to control it. So you have to close the well. Assume the aquarium is fully sealed. There is no air inside. It is full of water. And if you leave the air bubbles, the size of the air bubble is not going to increase. The size remains same. The pressure remains same. The size of the air bubble is going to be the same. It brings the same pressure from the bottom to the top, if in sealed condition. So there are two conditions. One is when you are allowing the gas to expand, when you are not allowing the gas to expand. So when you are allowing the gas to expand, the hydrostatic pressure starts reducing, inviting more heat. When you close the surface, you are not allowing the pressure or the bubble to expand. So it is going to come the same way. Because it is bringing the same pressure from the bottom to the top, the bottom hole pressure will start increasing. If you close the well and if you don't allow the kick to expand, that will take care of the bottom hole pressure. So the overbalance condition will be regained without doing any well control methods. You close the well. The bottom hole pressure or the hydrostatic pressure will increase because the air bubble is coming up carrying the same pressure. When the air bubble comes up, this pressure plus the drilling fluid pressure will balance the formation, and it will go to overbalance condition. So it will stop further influx getting into the well bore. It will control the kick by itself. That condition is called the stabilized condition. This condition has to be attained before you do any well control procedures. That is this. So our kick fluid moves up through the mud column. Minute gas bubbles expanding as they rise. Expanding bubbles contaminate a large section of mud column, thereby further reducing the hydrostatic head and allowing more rapid entry of formation fluids. So it aggravates the situation. So this should not be allowed. So you have to stop. You have to put a check. So you have to close the well. So if you want to close the well, you need some equipment, a blowout preventer, BOP, which is a main component which will close the well at the surface. So if you use the BOP to close the well, you don't allow the kick to expand, you don't allow the formation, more entry of formation fluid, so you stabilize the well. You don't allow the kick to expand, you put a check, you put a control by closing at the surface. So that BOP or the blowout preventer is a secondary well control method. Blowout preventer, the equipment what we use at the surface to contain the well or close the well, is a secondary method. Secondary well control barrier. So which is the primary well control barrier? We haven't talked about this. The equipment what we use at the surface is the secondary well control barrier. So the first well control barrier or the primary well control barrier is the drilling fluid what we are using in the well. If the hydrostatic pressure is maintained by the drilling fluid, it is always balanced or more balanced, so there is no kick. So the primary well control barrier is the drilling fluid maintained in the well bore with correct density and keeping the hole full. So the drilling fluid is a primary well control barrier and the BOP is a secondary well control barrier. So if you lose the primary well control barrier, you get into a kick. To control it, you use the BOPs and you circulate out the kick. When you close the BOP, there is no further entry. Whatever well fluids are entered into the well bore, you have to circulate it out without allowing any further influx. That is well control method. Keeping the bottom bore pressure constant, same as the formation fluid, you circulate out the kick, the unwanted influx out of the well, and make sure the correct density of fluid is inside the well to bring it back to balanced condition. That is successful well control. So when you open the BOPs, there should not be any pressure, there should not be any fluid. That is well control. If unchecked, that means if you have not identified the kick or if you have not taken any control, if you have not put a check, it becomes uncontrolled and the decrushing formation fluids expel the mud out of the hole. They throw away the drilling fluid, taking or going completely out of control, and that becomes a blowout. So before it becomes a blowout, you have to close the BOP, take control of the well, stabilize the well, and then circulate the kick out with a higher mud density. That is well done. So, if mud returns from the hole faster, then you are pumping into the hole. That is an indication. So this is an indication. It means how you detect the kick. How you identify that a kick situation has happened. That is you detect. You are pumping 250 gallons per minute inside the well bore. You are pumping 250 gallons while drilling. But if you are getting 280 gallons of drilling fluid, That means there is some pressure differences. The flow rate is higher. You are pumping 250, you are getting 280. That means something else is happening down below, which is pushing out more fluids. That is the indication. Then, pit level. You use a pit, drilling fluid. It is a closed system. The level remains constant when you are drilling. You pump 250 gallons per minute and you are getting returns 250 gallons per minute. So the pit level is the same. If the flow rate meter is not working, the pit level meter will give an indication that the pit level has increased or it is continuously increasing. That is the indication of a kick. When we get these are the two primary identification methods. Indications you get. The driller has to be watchful. If he gets an increased flow rate or an increase in pit level, he has to stop drilling. Check, is there any problems? It may be a false indication or it may be a correct indication. So depending on that, he has to act. So when you are pulling the pipe, if you are pulling faster, swabbing effect, you get into a kick. And every time you start pulling your pipe, you need to keep filling up so that the hole is always full. But without filling in, if the hole is full or if there is more returns, that means you have taken a kick. More support from the reservoir. So you have detected a kick. What you have to do? You have confirmed that you stopped the pump, but the well is still flowing out. That means the kick which has entered inside is pushing the fluids out without any input. You are getting output. That is a kick. So when you confirm the kick has happened, what you do is you stop drilling. That means you stop your pumps first for checking. The pumps are already stopped. You stop your rotary. Don't rotate your spring. Stop it. Pull the bit slightly up. Not up because you are touching the formation. Make sure you lift it at least a few feet above. And make sure your BOP can be closed properly. Not against a tool joint across a drill pipe. Close the BOPs. When you close the BOP, that means you have arrested the kick. You have arrested it. It cannot escape from the well. So you arrested it. Once it is arrested, it will start moving out, but you cannot go out of the well. If you don't close the BOP and if you start drilling, if the kick comes to the surface, that is a blowout. So close the BOP and wait till the pressures stabilize. Once the pressures stabilize, you start doing your calculations and decide which method you have to do and proceed with it. So now, we will recap what we have studied the last 5 minutes. So what is a kick? A kick is an unscheduled or unwanted entry of formation fluid or pore fluids into the wellbore. For a kick to happen, the formation pressure should be more than the hydrostatic pressure or an underbalanced condition. So kick happens in underbalanced condition. And why does a kick happen? The pressure inside the wellbore is lower than the formation pore pressure in a permeable formation, because the intensity of the kick is decided by the difference in pressure and also the permeability of the formation. If the permeability is more, the intensity is more. So your reaction time should be quicker. When this will happen, mud density is low, the fluid level is too low, or swabbing when you are pulling the pipe, or when you have lost circulation. When you lose the circulation, the fluid level reduces. And when you stop the pumps, ECD is low. ECD is nothing but equivalent circulating density. Even though you have a mud density, when you are circulating the fluid, because of the frictional pressure, additional frictional pressure in the canals, there is a slight increase in density because of circulation. That is ECD. We will cover it in the next topic. So, what is blowout? A blowout, or when it happens, a kick when it is uncontrolled, unidentified, and when it reaches the surface, it becomes uncontrollable and it becomes a blowout. So this is the theory behind the pressures about formation of fluid entering into the wellbore. Uncontrolled, it becomes a kick, and a kick control procedures. So the typical sequence of well control. First you identify the kick. That means a kick has happened. Formation fluid has entered the wellbore. Then you have to confirm it. You stop drilling, do visual checks. That means when the pumps are stopped, the well is not stopping. The well is still flowing. You are not pumping into the drill pipe, but the annulus is still flowing. That is a confirmation. So you have to confirm before you go to the well control method. First is identification or indication, then confirmation. Then you have to contain. Contain means you don't allow more influx to come inside. So this is where you close the BOP. So once you close the BOP, you are not allowing further influx. You arrest the kick. Next is the removal of kick from the wellbore and replacing the higher mud weight to balance the formation. This is the kick control procedure. This is just the indication, confirmation and containment. The next topic what we will see in the next hour is removal of